forces in motion, there are some pretty important equations that you're going to need to know for these. And these might seem like trivial and you already know them, but F is equal to ma is probably the most important that you're going to need to know. And I don't know how you were taught this, but I'm going to say like 75% chance that you were taught this in a way that is not correct. What this is saying is this is the total force on an object is equal to its mass times its acceleration. So what I mean by that, let's say we have a block, and the forces that are acting upon it are gravity, so we'll label that the force of gravity. There's a normal force because there's a table right here. So force normal, or some people will call it the force perpendicular. Let's say I'm pulling on it with a string with this force applied, and then let's say there's a little bit of friction going on right here. The total sum of these forces, so if I was going to add the force normal, and I'm going to put this little hat on top of it to denote that it is a vector. Actually, does anybody here not know what a vector is? I guess, do you know what a vector is? Yes or no? Yep. Okay. Cool. So it seems like everybody knows what that is. Some sort of magnitude and the direction is super important. So if I'm adding all of these vectors together, the force normal, the force friction, the normal force, and the gravitational force, all of these added together should equal to mass times acceleration. This does not mean that the normal force is equal to mass times acceleration. This is not true. Nor does it mean that the frictional force is equal to mass times acceleration. This is also not true. It is the total sum of the forces that is equal to mass times acceleration. So make sure that you know that. That being said, we can figure out what some of these individual forces are. So what you've seen me do, and I'll draw it again just so that it's clearer. When you have an object and forces acting upon it, you want to draw what's called a free body diagram. You may have started to do this, you may already know how to do this, but it's important enough that I'm going to tell you again. What this is doing is it's showing our object and all of the forces acting upon that object. So say we have a box, and the box is somewhere falling on Earth. I'm thinking to myself, okay, what forces are acting upon this object? And the very immediate one is the force of gravity. So I draw a line with an arrow from the center pointing downwards, and I label it F sub G. This is the first force that you should always label, and it's always pointed down towards the center of the Earth. Let's say we add a table. This object is not crashing through the table. It is not being propelled up by the table. It is simply resting on the table, which means that I should have another force that is counteracting the gravitational force. And I can know something very particular right here, is that the force of gravity, which I can write as m times g, m being the mass of this object, g being 9.81 meters per second squared, the acceleration due to gravity, this should be equal to the normal force in this particular situation. If, for instance, I took this force of gravity and then I took my hand and then pushed down on top of it, I would have some other applied force. But thinking about it again in a real sense, this object is not being pushed through the table. So that means that in this case, the force of gravity plus the applied force will equal to the normal force. The normal force will get bigger to counteract the extra applied force. You'll also see this normal force referred to as the perpendicular force. Sometimes you'll see it with this little line right here that sort of denotes that it is perpendicular. They're synonymous. They're basically the same thing. Okay, so if I have an object on a table with a force of gravity pulling it down, the normal force pushing it up, then I could apply some other force. And I'm just going to call this force 4. This is the fourth force acting upon this object. And then let's say this table is not perfectly smooth, so I have some frictional force. Now, the way that frictional force is calculated has to do with the normal force. And you don't need to know this little tidbit of fact, but the normal force and the frictional force are the exact same force. Because it's the table acting upon the object. For practical purposes, you don't have to worry about that. Just, they come from the same thing. The frictional force is equal to the normal force times some coefficient of friction, and we denote that with the Greek letter mu. Mu can be either kinetic, which means it's moving, so kinetic, we'll write that as mu sub k equals moving friction. And then the other one is mu sub s, which is static, which is still friction. That means it is not moving. You guys have probably done this before, but like if there's something really, really heavy and you start to push it, it takes a lot of effort. But then once you get it going, it's not as hard to push anymore. Most of the time, the coefficient of kinetic friction is higher than the coefficient of static friction is higher than the coefficient of kinetic friction. There's some objects where that's not the case. I don't know any examples, but I just know that there are. Usually this is a number somewhere between 0 and 1. It can be higher than 1, but it very rarely is higher than 1. So these are the important equations. I'll rewrite these just because this is really messy. The equations that you need to know is that the total force is equal to mass times acceleration. And I'll draw these with vectors because direction matters. The force of gravity, its magnitude is equal to mg, where g is equal to 9.81 meters per second squared. The normal force is most of the time going to be equal to mg, which is just the force of gravity. And then the force of friction is going to be equal to some coefficient here times the normal force. These are the important equations. Let's say that you're given a problem where instead of an object is sitting on a table like this, what if it's a ramp? And there's an object sitting on a ramp or moving on a ramp or something. Here's the strategy. You break it into two problems. So let's say our problem is we have a ramp and there's an object on this ramp. Obviously, there are two directions in this situation. There is down the ramp. Well, yeah, okay. There's up and down the ramp is one of the directions. And then there is this right here. If we were to draw a free body diagram, we would have the normal force being put like this, We might have an applied force like this, a frictional force resisting our motion. But here comes the problem. Gravity points straight down. And this is not a part of our coordinate system. So in order to get it into our coordinate system with our force normal, our force applied, and our force friction, we have to take the force gravity and we have to split it into two different portions. We'll have our force of gravity in the parallel direction, and we'll have our force of gravity in the perpendicular direction. And actually, why don't I draw those in different colors just so it's even more clear? So force of gravity in the parallel direction will be the portion of gravity that points down the ramp. And then the force of gravity, let's see, what other color do I have? Purple? Yeah. The force of gravity in the perpendicular direction is the portion of gravity that points into the ramp like that. If I look at this situation right here, I can actually recognize something that you might recognize from the last side, which is we have a line right here. We have a purple line that goes sort of like this. And then let's just take that blue line and shift it downwards. There's no reason we can't do something like that. Like that. And we know that this right here is a right angle. We have a right triangle, which means we can use things like sines and cosines. Now, usually, these things are labeled with the angle sort of like in here. I'll draw that in a different color. The angle is sort of in there. That angle is also the same angle as right here. So let me draw this a little bit more clearly for you. If you have your ramp with your object right here, and the ramp is at an angle of some angle degrees theta, then the angle between the force of gravity, the actual force of gravity, and then the purple force of gravity perpendicular is the same angle. I could prove this to you, but you could just take my word for it, that these angles are the same. So now that we have our right triangle, and I'm not going to draw it with different colors anymore just because it'll take too long. So let's say we have the total force of gravity here. We have the force of gravity parallel here, and then the force of gravity perpendicular here. And if we know this angle theta, we can figure out that the force of gravity in the perpendicular direction is just the force of gravity times cosine of theta. And then the parallel is the force of gravity times sine of theta. Be careful. It might look like this is backwards from what we normally do. And that's because we normally look at this angle right here. But instead we're looking at the top angle. And that's why your brain might think it's reversed or whatever. Yeah. Scale from 1 to 5, how much sense does this make? Be honest. Okay. So from the people who are responding, which thank you, it looks like we're having about an average of 4. Some people are understanding it a little bit better than others. Essentially, just think about it as the same way we were doing it last week, where you're splitting it up into 2 problems, except instead of x and y, we're doing it perpendicular and parallel, where parallel is parallel to the ramp, and then perpendicular is perpendicular to the ramp. It'll start you out on the introduction tab, which we will be using a little bit. You sort of have a little guy right here with an object and a ramp that you can adjust up and down. You can do it by clicking on the object, going up and down, or you can use the sidebar and slide it, or you can type in something. So 25.2. When you hit enter, it'll set it to 25.2. You can apply force to this object in 2 ways. You can click on the object and push it, and it'll push the object. Or you can use this right here, and it will also do the same thing for you. You can set the initial position of the object. So what this lab is going to start you out with is you start, and then you have to like adjust it up and down until it starts to move. Watch this. It's not moving at all, but it 100% should be moving. The trick to get it to start is to make sure that you've hit the play button down here so that the simulation is actually running, and then you can adjust it upwards and it will begin to move. Clicking on this sum of forces is something that I highly recommend you do, because this is the thing that equals to MA. And you can see that it changes based on a lot of things. And so it's nice to have. So this is the first tab. The second tab allows you to set the coefficients of friction yourself. You'll use this for like 1/10 of the lab. It's pretty easy. Same thing as before. This one is going to be used for like another 1/10 of the lab, but it's the like more important 1/10 of the lab. Same setup as before. You can set it to a position, you can raise it up or put it down, but you also have these graphs down here. It will start by only showing the applied force, but you can also add the force of friction, the force of gravity, the sum of all the forces, which you can turn that on up here as well. You can also find out what force is being applied to the wall, but I mean, it doesn't matter for this one. When you run the simulation and you adjust the thing, you'll see the graph change. Once it starts moving, it'll change. Once it's on the ground, it'll change. You can stop the simulation, and then you can adjust this by zooming in. It'll change your axes, and you'll be able to see different things right here. If you hit playback like we did before, you're not going to be able to, you will be able to adjust the time to see what values are where, because you'll need to record them. So this is the object as it's moving on the ramp. You can see the forces over here on the left, and then when it's on the ground, you can see the same forces on the left as well. And then when it has come to a complete stop, you can see that there are no forces that are acting upon it. Note that this force of gravity is the force of gravity in the parallel, which means it's the force down the ramp or across the horizontal. And I think when it's across the horizontal, we can all see that that gravitational force is 0. And that's the lab. You can change the object on the side right here. Same thing in the introduction down here.